Okay, so let me begin just by reminding ourselves where we got to yesterday. So yesterday we had to introduce quite a lot of machinery. There were a lot of definitions. I will try to restrict to doing examples after I've described a kind of a general approach to what we want to do to describing the action of automorphisms today. So hopefully won't be so many unfamiliar definitions today. Okay. So let me see where I want to get to. Okay, so let's just remind ourselves. Yesterday, we worked out how we transform our G vectors when we change the node or the seed that we're choosing as our reference seed, our base seed, initial seed. And the way we did it is we had piecewise. So we had these edge variables, I called them. So we had edge variables for node. So two nodes related by mutation. So we have edge variables for node T. Let's call them Z1 up to Zn. And actually, what I need to do is to remember, if I'm interested in the G vectors, I should work with the dual edge variables. So I consider the edge variables for the dual cluster algebra. So I think I denoted them by check. And then we had, similarly, edge variables for a node that's related to node T, call it node T prime. Here they are, again in the dual. And these were rational functions of the ones above. Okay, so by mutation, we generate rational functions of our original variables. And then what we said was, define this piecewise linear map. So we tropicalize these rational functions of these variables. So we tropicalize those rational functions, and we define this piecewise linear map, which takes the tropical versions, which are called V, just to remind ourselves that we've tropicalized. So these stand for these tropicalized variables. And it takes them to the piecewise linear map that I get, piecewise linear function of those variables that I get by tropicalizing this. I get this piecewise linear 1 prime. This was a piecewise linear map. And then we concluded that if we apply this piecewise linear map to our G vector for a given cluster variable in our node basis with respect to our initial seed T, this gives us G vector for the same cluster variable, but with respect to T prime instead. Okay, it's just the action of this piecewise linear map that allows us to change the reference seed. Okay. So what I want to do is use this in order to describe how we can think about automorphisms of cluster algebras. More generally, they're called quasi-automorphisms. Well, I'm going to do quasi-automorphisms. I'm going to discuss quasi-homomorphisms. So these were introduced. Notion was introduced by Fraser, 2016. And the idea is what we said in words yesterday, that there might be two seeds that have the same shape of the quiver diagram, let's say, but they have different variables at their nodes. And what we would like to do is define an action of homomorphism on the cluster variables that takes the cluster variables from one seed to the cluster variables for another seed, possibly multiplied by frozen variables. This is the quasi bit. And then what we would like to do is study what is the induced action of that on G vectors. So given a cluster variable in one cluster algebra with a given seed, and suppose I know what it is, can I compute what should be the G vector for the image under this homomorphism map, or automorphism map, if we're talking about the same cluster algebra? That's where we want to get to. Okay, so first of all, just the quasi bit. So if I have x and x prime, two cluster variables, then we'll say they're proportional if proportional, so x is proportional to x prime, if x is equal to m x prime, where m is a monomial in frozen variables. So remember, we might have a bunch of frozen variables that we never touch. They're in every seed. And we can say two variables are proportional to each other if they're the same up to this monomial in the frozens. So, all right, so if I take the cluster algebra and I map it to some other cluster algebra, then this map will be a quasi-homomorphism. If, well, first of all, it has to be a homomorphism of the cluster algebras. So it should map a free generating set to a free generating set. Potentially up to frozen variables. And moreover, there should exist some seed, sigma t, that's in A. So here it is, with data on it, x, t, y, t, and exchange matrix bt. And there should also be a seed sigma t prime in A prime with data x t prime, y t prime, bt prime that looks the same as the first one. So what looks the same means that if I apply x to the cluster variable, the ith cluster variable in this seed, I get that it's proportional to the cluster variable, a cluster variable in this seed. And I'm going to allow potentially for the fact that I might permute the node labels when I do this. So I'll allow there's some permutation pi I t prime. So that's the proportional bit. F maps these variables to these variables, possibly up to monomials in frozens. And it takes the z variables, these edge variables, and it gives you the associated z variable in t prime. And actually, you can argue is derived from these two. It takes the exchange matrix, so the exchange matrix of this seed has the same shape as the one up here. In other words, this exchange matrix is the same as this exchange matrix, again, possibly up to permuting the node labels. Okay, so this means the matrix whose ij element is the element pi I ij of B. Okay, and actually also, so we've allowed for this pi, there's also a potential sign that you can introduce. So let me write that. So there's a signature. I could have this inverted. I could allow myself to invert the edge variables. And if I invert the edge variables, I should allow myself, I have to correspondingly flip the sign of the B matrix. So epsilon can be plus or minus 1. So there have to exist all these things. It's possible to find two seeds that do this, and then your map acts accordingly on the cluster variables up to proportionality, mapping them into each other. It maps the edge variables, potentially up to inversion, and it preserves the B matrix, potentially up to flipping the sign.
Is this a definition?
This is a definition of quasi-homomorphism. Okay. Right. Now, what we would like to do is work out, given that we might have this situation, work out if we've got a variable which has some associated G vector to it, what would be the G vector associated to the variable under the image of this map? So, for example, if I have f of x equals mx prime, what is g of x prime with respect to some node in terms of g of x with respect to some node? I guess I should put prime there because it might be a node corresponding to A prime. Okay, so I want to know the G vectors in A prime, given the G vectors in A, assuming there exists such a map. Okay. And so I'm going to call it a quasi-homomorphism, but it will be quasi-isomorphism if you can do the other way around, such that essentially it inverses, or rather at least inverse up to this proportionality. So I'll have an isomorphism if I can find one that a G instead of an F, which goes in the opposite direction, obeying the same conditions. Okay, so let's restrict to this isomorphism case. And because ultimately I'm going to be interested in automorphisms. Okay, so here's the claim. So the claim is that okay, so there's one more small piece of notation. So if f of x is mx prime, I'm going to define h sub f of x is just x prime. I take the active cluster variable and I strip off the frozens and throw them away, just so that I record that I'm definitely at some active cluster variable for A prime. Okay, so then the claim is that G of H of F of X, or some node, call it T prime, is equal to this map that we introduced over there, this piecewise linear tropicalized change of coordinates on the z's, such that I relate the coordinates on node T0 to those on node T, do the tropicalization, and apply this to G at our chosen initial node T0 in A. And if I had this permutation, I should take the elements and apply the inverse permutation to the elements of that vector. Right, so good. Why did I call that T prime? That's right. So what sits where? Very good. So let me draw a picture, and then hopefully everything will be a bit clearer. So there are some seeds that are relevant to this game. So suppose I have a seed here, I'll call sigma t. This is in A. And suppose I apply this map to its cluster variables, then I'll get the corresponding seed in A prime, which I'll call sigma t prime. Yeah, so that's the image in this sense, that I can find a pair that does this. Okay, and suppose I'm going to ask myself to find G vectors in A prime with respect to this seed. Now I can always do that because when you impose this condition on the B's, either the B's are the same in the two seeds or they flip sign, but then any corresponding mutations that you do will kind of proceed in parallel because I've got the same B matrix. So not only will it be the case that this seed will map to this seed, but any mutation, as long as I do the corresponding mutation down here, those seeds will map to each other in this same sense. Okay, so imagine I do some mutations, some string of mutations, mu up here. This will take me to some other seed, let's call it sigma t tilde. Okay, and suppose I'm interested in a given variable x in A. So this is where x is going to live. X lives in this seed. So I find some seed where x lives. And I'm interested in finding G vectors with respect to this T prime in A prime. So everything up here is going to live in A. Everything down here is going to live in A prime. Okay, so there will be some other seed, since everything mutates in parallel. Sigma T tilde prime. So this map is the homomorphism. So this is HF or F. It maps the variables, active variables up here to active variables down here. Same here. Then if there's this permutation, I should do the corresponding sequence of mutations down here. So I mutate here on the same nodes, except we're possibly with permuted labels if I had this permutation. But there's a corresponding set of mutations that you would do down here to get to the seed that's the image of this one. Okay, so what does this formula say? It says, suppose in this algebra, suppose I was computing my G vectors with respect to this initial node. Okay, so the G vectors in this initial node, they'd just be the unit vectors. That's where in the initial node, we just put the unit vectors on there. Down here, the G vectors in this cluster algebra, they'll be the unit vectors because I put them on, I've declared this to be my initial node. And then these G vectors will simply map to these G vectors, possibly up to permutation. And then as I do the mutation, all the G vectors will change in exactly the same way because I've got the same B matrix. And so these G vectors up here will map to these G vectors down here up to this permutation of the elements. If I had to worry about the permutation of node labels. Okay, so that would be, so what's sitting in here? The only thing that I have to worry about is that maybe in my original cluster algebra, the G vectors that I was handed were not with respect to this initial seed. Maybe they were with respect to some other initial seed. So I should put some other initial seed, let me call that sigma t0, which is where I started. Suppose someone's handing me the G vectors, and they pick some initial seed, sigma t0. Okay, there are some mutations that will take me along to here. So this, what's in this bracket, is just the statement that the G vectors that I want, suppose I've got x in this seed, then h of f of x will be in this seed, and the G vectors would be the same if this was the initial node. So that's what this is, this whole thing in the brackets. But what's that? I just have to take into account this set of mutations here in A, which tells me that if I want to get from T0 to T, I should better tropicalize the change of coordinates that takes me from T0 to T in A. Okay, so that's why what you have here has this action of this piecewise linear map. This would be G of X T prime. T, excuse me. Okay, so I'm handed a G vector for X. Let's say it's in this seed, that's this guy, with respect to this initial seed, and I compute its image down here with respect to this initial seed. That's what's on the left. Does it make sense? Complicated, maybe overly complicated, but I think, okay, so the reason I thought I constructed it that way is if we suppose now we have an automorphism rather than a homomorphism between two algebras, all we have to do to this picture is identify A and A prime, and then remember if I'm an automorphism, I'd better be using the same reference seed before and after I apply my map. So all I have to do is identify an A and A prime and identify T0 with T prime. That's it, you're done. Okay, so it's not so complicated. I'm just saying, all I'm saying is to compute the thing you want, do a piecewise linear map that you get from change of coordinates and tropicalization, apply it to the thing you had, possibly permute the elements. Okay, so if we do automorphism, we just let A and A prime be the same, and T0 be T prime, and then this formula becomes simply that's just replacing T0 with T prime. So I'm calling my reference seed T prime. Okay, and what I've actually written down is the formula for epsilon equals 1, because I assumed here that when I did this, that the B matrix was literally the same to justify this sequence of mutations preserving the G vectors. But if I had the case epsilon equals -1, then what I would do is I would have to consider the opposite algebra. So here I've got G vectors that map to G vectors. I could, with plus tropicalization. I also have G ops, the opposite G vectors for the opposite algebra, map to the G vectors for the opposite algebra with the minus tropicalization. And if epsilon equals -1, they actually cross over. So the G's map to the G's for the opposite, and the G's for the opposite map to the G's. Let me not write the formula. This is the idea. Okay, so yesterday we did some examples. So let me remind you what we had in those examples. Example was, we did this A2 example. So that's here on the left. So our B matrix was 0, 1, -1, 0 on node T0. We started mutating. We concluded that after 5 mutations, we got back to where we were, except that the node labels were swapped over. We recorded all of the edge variables for each cluster in terms of the edge variables of the original. And yesterday I drew a box around some, but I've recorded it here because I didn't quite get to this. So this is what we recorded on the 3rd node of our sequence of mutations. And as a exercise 0 is to recover this and make sure you agree with the formula, I guess, if we're setting exercises. Okay, so this was the set of rational functions that we obtained. Now, given this picture, what I have to find, if this, I'm doing an automorphism, I have to find a seed that maps to my initial seed under the action of the automorphism that I'm interested in. And the automorphism that I'm going to think about is what happens when you map 2 stages down in that tree. So it maps T0, the variables from T0, the cluster variables from T0 map to the cluster variables from T2. Okay, so they map 2 stages down. And it turns out that if you do that, find that automorphism, the seed that maps to T0 is T minus 2. It's what would be up to, which is the same as T3, except that the nodes should be swapped over because the thing had a 5-cycle structure. So you can find this independently by mutating in the other nodes and going upwards instead of downwards when I did the mutations. So these are the rational functions in the algebra. They're also the rational functions in the dual, because this one's skew symmetric. So I don't actually need to take a dual here. It is its own dual. So these are the things I need to tropicalize. Take these rational functions, tropicalize them. So take this rational function. The tropicalization of it is minus the tropical denominator, which is minus V1 minus the maximum over 0 and V2. And here, I've got the tropical numerator, so it's the maximum of 0, V1, or V1 plus V2, here, minus the tropical denominator is just V2. Okay, so this is the piecewise linear map. And now, I guess exercise 1, take this piecewise linear map. I mean, I've written it out, so verify that this is what you get, and compute the action on the G vectors. So if we start on the G vector 1, 0, you find it maps to minus 1, 1. So this guy maps over here, which then maps down here, which then maps up here, which then maps down there, which then maps to where you started with, again in a 5-cycle. Okay, so we verified, we've got all the G vectors map to other G vectors, and it's a symmetry of the tropical fan that we got from the G vectors. Okay, so that's how these automorphisms work on these G vector fans. Okay, exercise 2 for the more hardy computer is try and do the general rank 2 case. So start with a B matrix that's 0B minus A, 0B A 0, with B positive and A negative. Of this. And then go to the start in node 0, where your variables are Z1 and Z2. You take upwards, I start on node 2, then do node 1 and obtain the node on minus 2, the seed from minus 2. Verify that these are the rational functions you get with some different powers, now A and B showing up. Take the dual of these. So remember, you need to take the negative transpose of B, okay, which is the same as swapping B to minus A and A to minus B. Take the dual of this formula, tropicalize, and then start computing the actions on some vectors. And I'm going to give, okay, so we know we have unit vectors in some node, but I suggest starting here, because you'll see some a little bit more structure. But start somewhere and compute the action of this tropical map. Okay, and then you should find there's some interesting special cases. So I've listed some interesting special cases that you might find for different choices of A, B. You find different types of behavior. So the case we just did there was minus 1, 1, the A2. There's also B2 and C2, which are dual to each other. And you will find that you should find that your tropical map gives you a 6-fold cyclic structure on both of these. This one's interesting. So this is with minus 2, 2. This is an affine case. I can just very briefly sketch what you should attain for the affine case. So in this case, you should find a tropical fan that looks like this. You have G vectors 1, 0, and 0, 1 in your initial node. There's also minus 1, 0, minus 1, and minus 1, 0. And then you should find that the action of your map, so if I draw this line at 45 degrees, all the integer points on here, you find the G vector. You don't have a cyclic structure. You've got infinitely many nodes with different variables on each node now. But you find that the G vectors follow this very nice regular pattern. And moreover, oops, I'm not drawing it very well. This should be integer, so these line up. Yeah. And the automorphism that you compute by doing this takes a G vector and moves it to 1, 2 further on. So for example, this one should go here. This one should go here. This one should go here. This one should go here, and so on. Okay, and then exercise, I can't remember what exercise that was that 2? Exercise 3 is do the case, what did I do? A equals minus 2, B equals 3. And then also think about fixed directions. Which vectors are fixed under the action of this automorphism that you get by doing this tropicalization? Up to, now I should write up to direction, so forget about the length. So, I mean, up to length, I should guess. Right, just the direction we care about. Modulo the length of the vector. Which directions are preserved by the action of this automorphism? There's one kind of clear, obvious direction that's going to be preserved in this picture, which is this guy that points up at 45 degrees this way. That's a fixed point. And you can sort of see, if I drew the vectors as, as rays coming out from the origin, you can see the rays are sort of piling up on this limiting direction, and vice versa from the other side. Okay, so different structure should appear for larger cases. Have fun encoding it. Correct. Oh, well, so it does matter what B actually is. So you just need it to have this correct sign property. But if I skew symmetrize, I will be restricting myself in terms of the kinds of mutation patterns that I get. So the mutation patterns depend on B, not just what you would get if you skew symmetrize B. So, yeah. Yeah.
Just your background.
So, okay. So, so you mean the actual action of the group?
Yes, exactly.
I don't know if there's an actual group action, but certainly it's related. It's yeah, and you can get, but you can also get the A matrix of the Cartan matrix of the relevant type from the B matrix just by putting some 2's on the diagonal and taking the absolute values of the entries, basically. So there is some relation between these, but I don't know if there's an actual relation of the Lie group, action of the Lie group behind it. There are probably experts in the audience who know better than I do on this question, actually. So, out now. Right. Okay. So I did all the rank 2 examples there. Mostly as an exercise. So now I want to come to Grassmannians. And then, okay, slowly we come closer to the contact of the physics motivation. Started off these investigations. Oh, and I should say, we had a paper with Jianrong Li and Omar Gurduan where we kind of fleshed out this structure and did some examples. So if you want to go and have a look in there and find some examples with formulas, all explicit, all the data written down, you can have a look at that. And that appeared in January. Okay. Now, okay, so let's talk about Grassmannians. Okay, so Grassmannians we can describe. So if I have Grassmannian GRKN, there are various ways you can think about it. You can think of it as the space of k-planes in n dimensions. You can encode it with a k by n matrix that gives us k n-component vectors that spans the k-plane. That specify a k-plane. But if we do that, we should mod out by the action of GLK, because we only care about the k-plane. So we should mod out from the left by some GLK action, and 2 matrices will be equivalent if they're equivalent up to a GLK rotation. It'll give us the same k-plane. And another way we can think about the Grassmannian, so if we think about the matrix, we can think about its minors. So imagine you've got k by k minors in your k by n matrix. And because they come from a k by n matrix, they obey certain relations called the Plücke relations. There are quadratic relations that these minors must obey. Essentially, that you cannot anti-symmetrize over k plus 1 columns, right? So you get quadratic relations between the minors if you try and anti-symmetrize over more than k columns. Okay, so there's various ways of thinking about the Grassmannian. Associated to the Grassmannian, or perhaps more correctly associated to its positive part. So you can make a restriction of positivity of the minors of our k by n matrix. And okay, maybe I should mean uniform sign, given that I'm modding out by the action of some overall GLK. But I can restrict the sign of all the minors to be all the same. And that restricts you to some particular subspace in the Grassmannian called the positive Grassmannian. Associated to that is a cluster algebra structure. So I'm just going to draw the initial quiver diagram. So it's a skew symmetric case. I can draw it with the quiver diagram with simple arrows. And let me just draw a particular example to illustrate. So I'll do GR3, see how far I get. 1, 2, 4, 1, 2, 5, 6. All right, so let's do GR3, 9. I have this initial quiver diagram where I put minors at the nodes. These are the basic variables. So imagine these each of these stands for some variable, which could stand in for the minor made up of the columns. These label columns in our matrix. Okay, so the active part of the diagram is going to be here. There are some frozen nodes, so this one's frozen. 1, thank you. And there's a bunch of frozens down here. Hopefully the general pattern for general K and N is obvious from just the labeling that I'm doing here. So I'm putting boxes around the variables that are frozen. And then some regular structure to the arrows. Describes the initial quiver. Okay, so hopefully it's kind of obvious how this continues. If you add more columns to get a bigger N, and you will add more rows to get a bigger K. Okay. All right, so these are going to be our cluster variables. And then the exchange relations that you get by doing mutations all follow or kind of essentially encode the Plücker relations of the underlying variables that these Plücker variables that describe the Grassmannian. So in particular, what happens is we saw you get, in principle, when you start mutating, you get denominators, right? We get rational functions of our initial variables in the mutation rule. But it turns out that as a sort of consequence of the Plücker relations, you can always find a Plücker relation in your numerator to cancel the factor that comes from the denominator. So if you use them, you start on each node, you'll always obtain a polynomial in minors as a variable on each node every time you mutate. Okay, so the cluster variables in this cluster algebra will be polynomials in minors of a certain type. And those polynomials will always preserve a positivity structure. So if I require an ordered minor in our K by N matrix, or a Plücker variable is positive, requiring fixed sign, because the mutation relation preserves positivity, every variable that you obtain by doing such a mutation will be also positive if we restrict ourselves to this positive region. All right, now an important role in what we described before was described by what I call these edge variables for each node. So let's just write out a couple. So in this case, we can compute the edge variables. All we need to do is take the product of the incoming arrows for a given node and divide by the product of the outgoing arrows. Yes? Oh, that's right. Yeah. So this is just the node for the initial quiver. And if I start mutating, I generate new variables at the various nodes that I get from my mutated quivers. And eventually you will discover all of the minors when you do that. And you will also discover polynomials in minors. And in this case, actually, I picked a case where you will have infinitely many such variables. Not a case which closes like the A2 case, where we just have 5 variables. Okay. Now, so the edge variable. So let's do the edge variable for this node. So for this node, we'll have incoming 1, 2, 3, 1, 4, 5 over 1, 2, 5, 1, 3, 4. And similarly, for this, the first node on the second line, we'd have 1, 2, 4, 3, 4, 5 over 1, 4, 5, 2, 3, 4. And you can check that for every edge variable, in fact, the diagrams are such that the edge variable you end up with is a rational function, and it's homogeneous in all of the variables for each column of the matrix separately. So not only is it homogeneous overall, but it's also homogeneous on each column separately. Okay, so we can think of these things, they're actually functions on the Grassmannian modulo the action of column rescaling. I can free to rescale each column. Okay, so I'll have n-1 such column scalings, because I already modded out by GLK, which contains an overall column rescaling for everybody. So there'll be n-1 more. So this space where these things live is this Grassmannian modulo the action of these column rescalings. That's going to be important when we come to the physics, because the underlying variables which enter our matrix are the momentum twisters for scattering amplitudes, and they live in a projective space. This is picked here GR3n, but the case of relevance for scattering amplitudes will be GR4n. Okay. So just to make contact with what we said before, then we have automorphisms. So there are some automorphisms for these cluster algebras, and there are some very obvious ones. For example, I can rotate all the columns around in the matrix, so there's an action of cyclic symmetry. So we can have cyclic. If I have the minor A, B, C, whatever it is, if I'm doing general K, this will map to, okay, I have to worry about some sign. Then I'll go map to A plus 1, B plus 1, C plus 1, dot, dot, dot. There's a reflection. So ABC, dot, 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 maps to, again, there's some sign I have to worry about. And then I flip the order and I do n minus C, n minus B, n minus A. There is a twist symmetry where, okay, if I take column WA, let's label the column of the matrix WA, and I flip it to the cross product up to some sign. So I have the cross product WA minus K minus 1 cross all the way up to WA minus 1. So I take a sort of K minus 1 fold cross product and I flip this vector to this cross product that you read off from the preceding columns. Okay, so there's some well-known automorphisms, and then there's some interesting ones that were also discussed by Fraser. An action of the braid group on this. This is only if K and N are not co-primes. You have such generators. For example, in this case, GR39. So we will have such braid symmetries in this example. Okay, and again, rather than, well, I'll write the formula, but let's describe the action on GR39. So imagine, okay, so think about these columns. I'm going to think of them living, so 3 by K matrix. Think of the columns as points in P3. Okay, so each column describes a point in P3. And I've got 9 of these columns, so let me draw 9 points. And I'm going to draw the lines that go through consecutive points. One, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is W1, this is W2, this is W3. Okay, so the action that we want to define, I can just draw as a picture now on this point. So we're in points in P2 because I'm doing GR39. So our columns define points in P2, which I'm drawing on the plane. Convenient to draw on the blackboard. You can sort of think of the positivity structure that we talked about as the fact that this polygon that I'm drawing is convex. Okay, because then, like, ordered minors, they all go around in the same orientation. Okay, so I can think of it as a uniform sign to the determinants. Okay, and now what do I want to do? So I have to define an action. So what does it do? It moves the points. So I'm going to define one operator that says, take W1 and put it at W2. But then for W2, maybe I'll put it in a different color. Okay, so for W2, what I should do is I should extend this line down here and consider its intersection with this line and move W2 to the intersection point, some new point out here, defined by the intersection of the line 1, 2 with the line 3, 4. And then 3 I leave alone and do nothing. And then 4, I just go around in lumps of 3 now. So 4 does the exact copy, jumps to 5. And 5 jumps to the intersection point of the line 4, 5 with the line 6, 7. 6 we leave alone. Seven, 6, 7 jumps to W8. W8 jumps to the intersection of the line 7, 8 with the line 9, 1. Okay, so this is braid generator number 1 does this. So in other words, W1 maps to W2. W2 maps to the intersection of the line 2, 1 with the line 3, 4. So we can write that as W2, 1, 3, 4 minus W1, 2, 3, 4. Okay, and then I repeat as I go around. And W3 maps to W3. Okay, and then I can rotate the picture of the red arrows by 1 unit, and I can define another generator, sigma 2. I get by rotating arrows. So one step. And okay, and that's the extra generators that you have in this case. And they're obviously related by a cyclic rotation. So I also have the action of the cyclic rotation, so I can get sigma 2 by conjugating by a cyclic rotation. Okay, and these generators obey the braid relations. And you could define a sigma 3 by rotating again. As I say, you can get all of these by rotating. Now, there's a similar picture for GR4n, but I'm not going to draw it. Imagine I drew a GR4n case. Okay, I could draw GR48. Since we do that, maybe it's... Just do the first one. So W1 will map to W2. And then W2, so what I need to do now is I have to construct the plane. So this is 1, 2, W3, W4, W5. And I consider the plane 3, 4, 5. So imagine now I'm in P3. And I can have a plane specified by these 3 points. And then I find the intersection of the line 1, 2 with the plane 3, 4, 5 here. This maps to this intersection point. And then W3 does nothing, W4 does nothing, and then I copy around for W5. Sort of lumps of 4. This is GR4n, GR48. Okay, so now we can just do, since we've got an action, we can do all the same games that we did just before in the rank 2 case, in this Grassmannian cluster algebra case. Just the computations are considerably heavier. So it's convenient to use Mathematica if you want to compute these piecewise linear maps. But it's not complicated. So the way to do it since we know the action, all we have to do is take the z variables in our initial seed. Now remember, we're meant to find a seed that maps to our initial seed under the action of the automorphism. So actually I should write down the inverse transformation to the one that I wrote down there if I care about sigma 1, or I could write down this and compute the action of sigma 1 inverse on the g vectors. The inverse, you just point the arrows the opposite direction. So the inverse is the same as the opposite to the picture that I drew there. And then all you have to do is act column by column on here with this map. And you will obtain a new rational function in minors. And it will be homogeneous just like this one was. Okay, so you can compute. And then what you can do, so there's a convenient parameterization. So, okay, there's a particular parameterization of the k by n matrix. You not specify what it is. Let's say in this 3 by GR3n case, starts off with an identity matrix, and there's a column of 1 minus 1, 1. And then, okay, then I should put up here, I should put the z variables, the edge variables, associated to the 1, 1 corner on the quiver diagram. I'm going to give them these 2 labels to show which node they correspond to. Okay, there's some explicit matrix. such that if you evaluate on this matrix, these minors, as minors of this matrix, you get back these z variables. Okay, so that's just, they're defined to do that. Okay, so then all you have to do is compute the action of this on your z variables. You get a new rational function that's homogeneous on each column in minors. Evaluate on this matrix, and you get a rational function of these original variables. And that's the rational function you want to tropicalize. Having tropicalized it, you can compute the action on all the G vectors in the cluster algebra using the formalism that we just described before. So slightly cumbersome to do it, but for example, just to give you an explicit example, so if I do in GR39, and compute the action of sigma 1 inverse on the second row, fifth column, edge variable. I've picked one which is particularly simple. Get this simple rational function. That's the thing that I want to tropicalize for that entry. And I do the same for every entry, every variable in every node in the quiver diagram. Okay, and then we get the action by tropicalizing that map with plus convention or max convention. We get the action on the G vectors, and it gives us the G of the active variable generated by the action this symmetry. Okay, so given a G vector, we can easily compute its image under this automorphism symmetry. Okay. Right, so now we can do, let's just imagine we've sat down with Mathematica and we've coded it up, and we can just start playing about with these transformations. We can do what I asked you in the exercise up there. Imagine now you just pick some random vector. I don't know it's a G vector or not. Maybe it is, maybe it isn't. And I act with this piecewise linear map that I've generated, and I just keep acting forever and ever and ever. Iterate its action. You find that it will go off in some direction, and eventually the direction will stabilize, and it will pick out some preferred direction. And if we're talking about GR39, it will be in a 10-dimensional space because we had 10 active nodes. Or in GR48, there's 9 active nodes, and you get some preferred direction in that space, which is where we end up pointing if we keep iterating this transformation. So once we take that direction, we find a fixed point. Okay, so mod out by the length, don't care about the length, and find the limiting direction. Okay, all right. Exercise 4, which I'm not really expecting you to do because you would have to sit down with Mathematica, encode these formulae, and obtain the explicit rational functions, and do the tropicalization, and then repeat the action of this generator. So, but fun if you want to do it. But let me just write down what you find. So for GR48, you do that, you find some interesting limiting direction. We call it G1 infinity because it's kind of a limiting direction that you get. It's not a G vector in the cluster algebra, so it doesn't correspond to any cluster variable, but it's some preferred limiting direction, and it's very simple. You find it's a vector of just 1s and -1s and 0s, and if you trust me, this is what you get. Okay, where I've picked an ordering where in the diagram that I wrote, I read down, so this is the top left This is underneath it, that's underneath it. Then the second column, underneath it, third column, underneath it. So that's the ordering I picked in order to write down, to label my nodes. I have to write down a vector, I have to tell you what order. So this is the limiting direction you find. Okay, so very good. On the other hand, we've got more than one generator. So here we had sigma 1, sigma 2. Here, we've got sigma 2, and there's also sigma 3 that I can get by rotating again, and in principle, sigma 4 that I can get by rotating again. And I'm saying in principle because you can in fact generate a cyclic rotation through, in this case, sigma 1 and sigma 2, and in this case, sigma 1, sigma 2, sigma 3. So if I give myself a cyclic rotation, there's really only one generator to worry about. But you also have the action of cyclic transformations, which you can also tropicalize and compute the action of. However you want to do it, either by computing the fixed point for sigma 2 or by applying a cyclic transformation to this one, you find another limiting vector. This is the fixed point of sigma 2. And again, simple. That's interesting. So we had these two generators. Sigma 3, if you do sigma 3, you recover this one again. Sigma 4 will give you this one again. So you don't get anything more by considering the basic generators. And this is a cyclic transformation. So I don't get anything more out of these by considering cyclic transformation. However, even with sigma 1 and sigma 2, there's something else I can do. I can take this one and apply sigma 2 to it. Now I generate something new. Right? There isn't either of these fixed points. So this thing, you can act with sigma 2 and generate something new. Like this way, this one, you can act with sigma 1 and generate something new. And then you can start acting on those with the other generators, and you generate a whole orbit under the full automorphism group of these limiting rays. Okay. Yes. Oh, I am at 70 minutes. Okay, good. Thank you. I'm meant to have 75. That's okay. Good. All right. So, all right. Good. So now we come back to some stuff that you can do with this. So you can classify this orbit, and you can count how many objects there are of each of these objects. And there's something I didn't have time to tell you about, but you can associate to these things that are not cluster variables, but they're also polynomials in minors. And I'll probably show you another way to do that. I guess that will be next lecture. And then you can classify these objects by the degree of that polynomial, and you can calculate them. And there's another way where you can represent these things as semi-standard Young tableau. And then you can just compute all the semi-standard Young tableau up to a certain degree, a certain number of columns. And you can also associate the semi-standard Young tableau to the cluster G vectors. Remember, these are not G vectors, right? I got these by this limiting procedure. But there's also a way to take the G vectors and associate these. And then I think it was a computation of Jan Rong and Nick Early, where you computed all of these semi-standard Young tableau, classified them up to some huge degree. And you observe that they're all cluster variables except for a class that appears only at every even degree, and this starts at degree 2, and there are these two at degree 2, and then there are these ones appear at degree 4, and there's some interesting counting given by degree. And the counting, so if I take GR48, so the number of these non-G vector rays that you can generate that correspond to a given degree R is given by, so they're all even. So if R is odd, There are none of them, and there's twice the Euler-Totient function of r over 2 if is even. So one of our motivations for studying the tropicalization of these automorphisms was try to explain this counting of these extra rays. And you can show, indeed, that you just get this orbit of this limit rays, and then having computed this and computing the restriction of the automorphisms to these generating rays, you find that all of the limiting rays lie on particular subspaces in this big 9-dimensional space. They live on 3 2-dimensional planes. And not only that, you can ascribe them to some lattice of points from counting, where the picture is, you can go and look at the picture in our paper, but when you do so, it becomes clear why there's Euler-Totently many at a given degree. I won't go through that, but that was one of our motivations. Okay, and all right. So our second motivation, which is basically, I think, what I'm going to have to describe in the third lecture, is what are these things? So our original motivation, before getting interested in automorphisms, thinking about Grassmannian cluster algebras, was that they seem to show up in the structure of scattering amplitudes in describing their singularities. And when you start at low multiplicity, so I drew the picture for GR39. I could have drawn the picture of GR48. If I take GR46, that corresponds to a 6-point scattering amplitude, and it turns out to be a cluster algebra of finite type, corresponding to the A3 type that we drew yesterday. If you take GR47, you get something that is, again, finite type, and it corresponds to an E6 diagram. And then you take GR48, and you get something that's infinite, but finite mutation type, and it has these automorphism symmetries. And you find that there are certain infinite directions of mutations that take you off in these directions, or equivalently, they're fixed points of these automorphisms. And these things actually correspond to variables that are not rational in the cluster variables. So you can associate certain natural square root objects to these limiting rays. And in the next lecture, I'll try and describe a bit more about how that comes about. And basically, the next lecture will be going through the physics and amplitudes motivation of studying these Grassmannian cluster algebras. Okay, so I think that's, since I'm at the end of my time, that seems like a good place to stop for now.